The PN junction is made up of two types of semiconductors, the P-type semiconductor and the N-type semiconductor. The P-type semiconductor consists of dopants that have holes which serve as charge carriers, whereas the N-type semiconductor is doped with dopants that contribute extra electrons into the semiconductor. Once we put the P and N-type semiconductors together, some of the excess electrons from the N-type semiconductor will diffuse over to the P-type semiconductor. When that happens, you end up with positive ions on the N-type semiconductor near the interface and negative ions near the interface on the P-type semiconductor. As a result of the existence of these ions, an electric field is formed. This electric field prevents the further flow of electrons from the N-type semiconductor to the P-type semiconductor. Electrons tend to travel opposite to the direction of the electric field. This region, we call it the depletion zone or the depletion region. So there will be no more free charge carrier here. If we were to attach a positive terminal of a battery to the P-type semiconductor and the negative end of the battery to the N-type semiconductor, the electrons in the N-type semiconductor could possibly gain enough energy to overcome the electric field. When this EMF is high enough, electrons will flow across from the N-type semiconductor to the P-type semiconductor, therefore closing the loop. This PN junction therefore serves as a diode in the forward bias direction. If we attach the positive terminal of the battery to the N-type semiconductor, the electrons in the N-type semiconductor will be attracted towards the positive terminal, therefore leaving more positive ions. More electrons are supplied at the P-type semiconductor end to fill up the holes. The depletion region expands. Current is unable to flow, therefore this PN junction behaves as a diode in the reverse bias direction.